All right, guys. So welcome to another class. It's always off when I come slightly late. So several things. Do you know about the final exam when it's due, and have you received a copy of it? Correct? You have received a copy of it. In particular, you have received notification of where to find a copy of it, and that is on my website. Good. Everyone knows that it's due on Monday. I think I said 22nd. I don't remember which day I said. Try to get it on that day. If it's really important, you might have a few more days, but bear in mind, I must post all grades by the 27th. Right. So, and I will try to post them earlier than that, but the earlier I can post them, the better. Good. And possibly next class, you know, the exams are due on Friday. So if you would like, next class, we can discuss solutions to that exam too. And you should begin whenever you are done with the exam too, begin solving final questions. I hope it's not hard, but it's hard for me to tell, right? I mean, I think I did not ask you hard questions. Maybe you looked at it. I kind of almost, there are so many questions I wanted to delete and I didn't, right? Because I thought there was mediocre questions. So I hope that means that they are easy questions. When is it due? It's due Friday night. Good. So back to the topic. Friday night. So again, we began learning about cumulative distributions for several random variables. So it's called joint distributions. And we noticed that if you define the cumulative distribution as FAB, then it's just X less than or equal to A, Y less than or equal to B. That's the joint cumulative distribution. And in principle, one can answer every single question about distributions based on that information, correct? So those are examples I gave you already. I hope I don't need to go over them again. And you had this table. That's how in practice it might work. I don't need to go over the table as I did it last time, correct? You'll remember this material. And I promised to explain a little bit about the way the density function is defined. And when I think of two-dimensional density functions, I even have this toy here with me. I bought it for that very purpose. You all know this thing, yes? Here, maybe I will stop sharing so you can just look at me better. All right, can you see it? I mean, I'm hoping that means that I'm now biggest of all. Am I the biggest of all, or it's not really the way it works? Yes, so this is an example of the distribution. So you see, you have this rectangle and there are many tiny pins. Here are the tiny pins, here they are, right? And those tiny pins are now no longer rectangles. What are they now? They are columns, right? So they are boxes, tiny thin boxes, and those boxes have width, length, and height. And at any given location, at XY location, f of XY is the height. Dx is the width, dy is the length, let's say. And together they make a volume. and volume is structured to represent the probability at a given location. So basically, how do I interpret fx y dx dy? So I imagine that this is a very a small square base on which you erect a skyscraper. And the skyscraper, statistically, you can imagine simulating it at least, right? The skyscraper is going to be, the higher it is, the more likely that box to be hit. So maybe what it is just you're throwing darts, right? And when you throw darts, you have many pixels on this box. It's like there's also many pixels, you see? And each point, it's not really a point, it's like a small blue square. And if you hit that blue square, it presses and it elevates it by 1 unit. Let's say if it's 1, you know, and then different places that are hit are elevated by different amount. And that's what would form the skyline. That would form the function f of xy, correct? You see, just like we did for rectangles, it's simple to imagine how the skyline is formed to have this interpretation. So it's called density function for that reason, as it indicates, the height indicates not the probability, but it does give you a sense that the higher the f, the more this point is hit, the more likely the value is to be selected, or near the value to be selected, to be precise, right? Each point xy has 0 probability of being selected, but if you discretize, each point xy is standing for an entire rectangle, just very small, right? So really, I think of this full expression as the probability, which is not 0 if dx and dy are not 0. Right? And then, of course, by that logic, it's all you have to do is just add up. So when I say probability x less than or equal to a and y less than or equal to b, what am I doing? I'm adding the boxes, right? I'm adding those boxes that correspond to y being less than b and a less than a. Do you see those are boxes, correct? Because x varies from -infinity to a and y varies from -infinity to b. So you can see it's just a grid. And I'm asking what's the probability of selecting a point in that grid. And what do? I add up over all tiny tiny skyscrapers, f of xy dx dy, and that's what this summation is really doing. So the reason you have double summation, just you add up, you can just decide how do you carry out this addition. You see, so if you first sum it like this, it means I first add up all those functions with the dx, and then I multiply by the y and add it over the y. You see, just the way you arrange the summation. But really, it's just the same as ordinary summation, nothing more difficult than that, just in the limit. That's why your integration, if you think of it this way, it's not so difficult to comprehend. And of course, you can see that if I have the cumulative distribution, I can take derivatives and I obtain the density function. Yes, and then here is an example. So suppose that we have this function. So this is my density function. And then I want to calculate the probability that x is bigger than 1 and y is less than 1. What am I going to do? I'm going to integrate this function from 1 to infinity on the x and from 0 to 1 on the y, and that's what I get. This integral I can split, just conveniently split into 2 integrals. Because here, why can I split it into 2 integrals? Because of the same reason I can factor a foiled, I think you call it foiled, right? I can factor a foiled summation. I just factor one part out of the other. You can see that because the x part, the x function and the y function can be separated, I can separate this times dx from e to the minus 2y dy. I can separate them. And then I have 2 separate sums multiplied by one another. And the result is just calculated, and this is what you get. Good. Wonderful. So then we have part B. Would you please set up part B just in the text message? Perhaps you can tell me when I set this as an integration, x varies from what to what, like x between one value and another value, and y between one value and another value, right? So that I see that you know how to integrate it, and I will show you how to do it. So go ahead, take a minute. For both of them, it would be nice, right? Because the X and Y are related. Okay, be careful. So it's not bad that I actually asked you that question. Well, X cannot be going from 0 to X because it's self-referential to X. All right, so let me now tell you about it. So here is that integral. So you can see what happens here. First of all, if X is less than Y, here is the line Y equals X. That's when they're equal. Yes? So I decide to represent it as follows. I say, okay, well, let me allow Y to be whatever it likes. So Y is from 0 to infinity. Yes? And then all that must be the case is for any fixed Y, here it is. Here is a fixed Y. For that fixed Y, X cannot extend bigger than that Y. So this is where X is equal to Y. This is where X is equal to X. You see, this is just parallel. I just drew the line over here as well. The X value is this integral, right? This integral. So X ranges from 0 to Y. Do you understand? Correct? It's easy to picture. Yes, it's like you have to remember how you cut how are you cutting the cake. So we can add it like this. We can add it for any of, we can add first over y, and then for each y, x never exceeds y. So that's the line. So carrying out the integral, of course, what do we get? We get 1/3. Yes. We get 1/3. One second. So what else is, let's say we have probability that x is less than a, x less than a. It's similarly just now it's only x. You see, that means that y can do anything it likes. Y can be between -infinity and infinity, and x is between -infinity and a. And when we carry out the integral, what do we get? We get 1 minus e to the minus a, and that completes the work. Yes. And then here is another question. Disk is of radius r. It is, and then we want a point is just xy is randomly chosen. And randomly means that every point is equally likely to be chosen, which means that if I discretize the disk r is just x squared plus y squared less than or equal to r squared, right? If I discretize it, that means it consists of lots of small squares. And over each square, I have the same altitude for the skyscraper because each square is equally likely to be pressed, which means my function, my density function is a flat plane in this case, right? It's now a flat plane. So it looks like a cake. And on top of the cake, you have this disc-like cap. Good. So the question is, first of all, of course, what must be the height of this cap? What is C, please? Determine C. Write to me what is C as fast as you possibly can. Now you don't need to, what is it, integral? You don't need to integrate it. You can right away figure out what that cap is because it must be the area, or sorry, the volume must equal to 1 by probability, yes? Why the integral must be 1? I'm sorry, guys. You see, as I am trying to answer your questions, I am trying to, before the countdown, I have 49 minutes remaining on this battery, and I cannot connect it to the electricity. It just doesn't work. And I cannot figure out why. And maybe it's because bad luck, and my bad luck, I mean my black cat came into this room. And as soon as that happens, yes. So just, you know, you never, that's what we mean by randomness and probability. Things just happen. So I'm tremendously irritated, and I'm trying to figure out where is the source of the problem. So here we go regarding this regarding the C integral. What is the C? It should be the integral has to be equal to 1. Do you agree? The volume, the probability, if I'm selecting always a point within the disk, the probability I'll select one of the points from the disk is 1. So that means C has to be such that if I integrate over the full disk, I will get 1. Now, if I integrate over the full disk, what am I going to get? I'm going to get C multiplied by the area of the disk. Am I right? And the area of the disk is pi r squared. Yes, which means what? Which means C has to be 1 over pi r squared, because it must correct the area to 1. It must multiply the area and make it equal to 1, everything, correct? So the altitude of every skyscraper in this scenario is 1 over pi r squared. Good? Yes, of course. So C, just think about it, guys, right? Think about it. Think about it. Here is that disk, yes? And what you do is you select a point in it. You select a point. Here's a point, here's a point, here's a point, right? The probability that you will that the point will belong to the disk is 1. Correct? Probability is just merely equal to 1. But what is that equal to? That equals to the integral of C xy dx dy over d. Now, sorry, there's no f of x. That is C. C is that dx dy. Yes. So what should that be, right? So if I remove the C, if I just take the C out, what are you going to be left with? You are going to be left with just the integral dx dy or dy dx, doesn't matter, over d multiplied by a constant C. What is this? This is equal to, it's equal to what? It's equal to pi r squared. That's just the area of the circle. So what is C equal to? C must equal to the reciprocal, right? So C multiplied by pi r squared is equal to 1, which means C is equal to 1 over pi r squared. Yes? Yes, each point in the disk is the universe. The area of the disk, just basically the integral. It's because why is the integral equal to 1? We're calculating volume, but But volume, where the height is 1, if I factor the c, the height is 1, it's the same as the area. Do you agree? So volume of the cylinder where the height is 1 is the same in number as area. I hope that makes sense. Yes. It's like if you have a rectangle and you put unit squares or unit cubes on top of it, right? So what's going to be the volume? The volume will end up being the same as the number of rectangles or tiles you can lay on the platform. So that means that even though it calculates volume, the number is the same, because the number of squares or square tiles you can place on the rectangular floor equals to the number of cubes you can place on the floor. Right. And if it's a circular region, you can just imagine that the cubes are very small, and that's an approximation. So it's still very similar idea, right? So you can imagine digitized version of it. So still the number of cubes you can place on top of this disk of height 1, if the cubes are of height 1, right? It's the same as the number of tiles, areas, you know, of 1 by 1 tiles that you can place on the disk. Good. Give me 1 second. All right. I was able to reconfigure it. It works. At least now my battery is charging. You see? Maybe now I'll be able to actually think about what we're talking about, really, right? I'm on autopilot. So, okay, guys. Are you still with me, guys? I mean, I have also a sense that maybe you don't know Calc 3 too well, or integration, or double integration so well. Am I right in my sense? Yes, well, it's not hard at all, guys. If you want me to give you a crash course in integration, please be happy to, right? I think it's not very long. I mean, you just have to think of integration as addition, and if you do it sufficiently well, you will be able to figure out pretty much lots of formulas. It's inside out how you do it. What do you mean? You don't need to draw them. I mean, unless you really want the S to be very beautiful, right? You just have to picture what's happening abstractly in your inner eye. Mm-hmm. So, okay, but you can do that if you just for some of them, but you need to really draw the idea. So it's not important how the actual integral looks like. Okay, so here is the next part. Okay, so now I want you to compute the probability that L. Well, actually, first we want to find the marginal density of X and Y. So marginal density means I just want to know just the probabilities of X alone. I mean, I'm ignoring the Y coordinate. I want to know how X is distributed. Make sense? So in other words, whenever I generate the point X, Y, I delete the Y information. I just record how many X's I get, how frequently. Okay. So how do I do that? Well, you agree that what I need to do is, if I want to figure out, let's say, the cumulative distribution of X at A, that means probability that X is less than or equal to A, that means that Y can do anything it likes. Good. And that means what? That means Y is less than infinity. But the only Y that can actually exist are for any fixed value of X. If you fix a value of X, you see, how do I get this this region? Let me possibly draw it for you. So if you fix the value of x, let's say here is your x, right? Now, what can y do? Y for that fixed x can go all the way to this point and start from this point. So what is this point? This is root r squared minus x squared with a minus, and this is root of r squared minus x squared with a plus, correct? So I can organize based on a fixed x. I know that for a given fixed x, this is the range that y can take. Good. And now I want probability that x is less than a particular value. So let's picture this. Okay, what is x less than a particular value? Let's say here is my value a. Right? So what do I want? I want this region, which I'm deliberately drawing in those lines. You see this region I can describe as lots of vertical lines. Yes. Now, what are you doing when you're adding integrals? It's like you're adding small squares. They're small squares, right? So the way I'll add the small squares, I'll add them based on one line, and I move to another line. So what is the inner squares here, right? So what are those squares? Those squares are the integral for any particular x. So this is this is for a fixed x. Let me actually write it in black. For any fixed x, I have this integral. I have the integral from minus root r squared minus x squared all the way to root r squared minus x squared, right? And then whatever is the function I'm integrating, fxy, right? And then dy, right? And dx. Okay, that's how I see picture. What is the dx? The dx is this part. You see, this is the dx. Everything is multiplied by the same dx. Do you see that? Now, what I do is, in essence, I'm just adding this height and this height and this height and this height, and not just the height, this region. You see what I do? I just take this length, and I find, when I say the integral, I find the part of this function. You see, this is the altitude at that particular xy. So if this x is fixed, you see, I just find the altitude corresponding to this fixed x and varying y. And fxy dy is just speaking about a generic rectangle over here. You see, so if this is actually position x, then what is this object? You see, I look at this small square, and actually this is just a view from above. If I turn it to the side, it looks like this, right? It is a sort of like a prism. Yes. Now this turn to the side. This here is my dy. You can see next you would have an x dy. Also, it's a bunch of dy's here, right? So, and then what is the altitude? So the altitude over here. Let's say this altitude. What is that? More or less, this altitude is fxy, correct? I imagine it's like lots of tiny boxes. So its altitude is f of xy. Then what do I do when I add them up over here? I say, okay, it's f of x dy multiplied by dy dx. You see? And the first summation is what? You see, the first summation is just for a fixed x, for this one fixed x, I add all of them up. So I add all of them. You don't see the altitude here. It's a view from above, if you understand me, right? So this is the part you don't see. So I just add them up over this x. Then I move to a different x and I add them up. So it means that then I have to add each of those additions. I have to add over all possible combinations of x, and those are from x equal to minus r all the way to a for this integral. Is it coming back to you? Do you understand what's happening, guys? I'm hoping I am using the right words, because the idea is so very intuitive of why the integral is like this. Chiara, yes, does it make sense? It's just the inner integral is just a summation along a column, and then I say sum over also all the values of x. It just means move to another x, move to another x. and that's in the limit. So when I say that, I imagine that actually it's discrete. I imagine that you have those strips, and there are just finitely many of them, so I can move to a different X. Good. All right, so then integrating it, what do we get? We have this integral. You understand how I got it. This function just happens to be always the same altitude, which is 1 over pi r squared. And when I integrate it, I just see that I just get this expression, correct? I just get this expression. That's my cumulative distribution. I don't need to go further because I'm going to find the density function. I want the marginal density. I take its derivative with respect to a, and that's the same as just taking this a and plugging instead of x, right? So what do we get? We get this expression. That's the marginal density at x. So I eliminated y, and I created a distribution for just x by itself. And because of symmetry, of course, you can imagine that here is the distribution. When I don't use a anymore, I just convert it back to x. Here is the distribution. Here is the density function. Then for y, it's going to have the identical formula. Yes? Why did you all disappear, by the way, my friends? Turn on your cameras. I feel blind and lonely this way. Well, I know, I appreciate Camille, right? You are my last window to the outside world, so to speak. Aside from that, all I see is darkness. All right, and then let's talk about C. We want to calculate the probability that L is less than or equal to A, where L is the distance. We can create different functions. L is the distance to the origin, okay? So do you understand what this is asking? So when I create random variables, I'm just relabeling the original points, right? So what does it mean when I speak about L? That means in terms of the points within this circle, it means that I can take. You see, I can just redefine. For instance, you see all of those points that you see here are. All of those points on this smaller circle are all labeled as, let's say, L equal to A, because they're all at the same distance. So it's just when L is just a relabeling of the same points, correct? So I want to understand what is the cumulative distribution for L. So I want to know what's the cumulative distribution of L, which is the probability that L is less than or equal to A. So what am I asking? I'm asking what's the probability that I have that I'm within circles. So those are all circles up to the circle, right? So it's a disk. So probability that L is less than A, it just represents the disk region. The way it represents it is the way I imagine it is it's lots of concentric circles, many concentric circles. You don't need to see it. So it describes the disk region, correct? So what's the probability I obtain a point within this disk region? And that probability is, of course, easiest to calculate because, again, this is uniform distribution. Easiest to calculate by just measuring the relative area of the small circle to the total circle. Just like with the intervals, it's the same idea. It makes sense, I hope. Yes, guys, do you see why that is the case? Just because the probability is directly proportional to how much space you occupy, because the altitude for all points is the same. It's 1 over pi r squared. Yes. So it is easiest to just say that. What is this? So this is just equal to pi a squared divided by pi r squared. So the answer is a divided by r squared. Agreed? So that's what we just found. So we calculate the probability that L is equal to A. Do you have questions, guys? Are you integration, the ideas, are they okay? So the next part is I want to calculate the expected value of L. Okay. So there are several ways of doing that, but one better way that actually I didn't put in my notes, maybe I'll do the better way first, is, I mean, how many forms for the expected value in the continuous case do you know? Are you aware of this formula? So the expected value of a random variable x, let's say, assume for a moment that x is bigger than or equal to 0. So the expected value of x will be the integral from 0 to infinity of x fx dx. You agree? Where fx is the density function. Good. Now this has a convenient another form, which sometimes it's going to be making integration far easier. So this is the same. I can make it into a double integral. So it's the same as integral from 0 to infinity. The integral from 0 to x fx dy dx. You agree? I didn't change anything. If I deal with the inner integral, I will have the x back in its correct place. So I actually move to the double integral. Now, do you see the frying pan? It's from 0 to infinity, 0 to x. That means y goes as far as x. Yes? So how do I reverse it? I can easily reverse it by saying, oh, it's the same thing as y going from 0 to infinity. You just have to picture the frying pan. Do you see it's a triangle? It means that for x going from 0 to infinity, y bounces all the way to the line y equals x. Yes. So the other way of describing it is this is cutting the cake by vertical slices, but you can also do horizontal slices, correct? So I'm going to do horizontal slices. That means that y is from 0 to infinity. You understand what I mean by horizontal slices, or should I draw it? And x is so x is from so x has to be, so it's horizontal, so x is from y to infinity, and that's fx dx dy now. Good. And what is this? This is, look at the inner integral. The inner integral is the probability that x is bigger than y, right? So this is the integral from 0 to infinity, the probability that x is bigger than y. It can be, because it's continuous, you can say bigger than or equal to, you can be free about the point y because it doesn't contribute anything if it's continuous. Be careful, right? Continuous, I can be saying bigger than or equal to, or bigger than, it's up to me. It's whatever I think is easiest. So it's this, which is what? Which is the integral from 0 to infinity of 1 minus the cumulative distribution of x at y dy, which is of course the same as the integral from 0 to infinity of 1 minus the cumulative distribution at x dx. I just moved it. Y is a dummy variable. There is no y or x. Yeah, what it means is that if I want to find the expected value, I just need to integrate 1 minus the cumulative distribution, or it's also known as the survival rate function. It means that it's the opposite of the cumulative distribution, very much related, you see. So the cumulative distribution is very nicely used for calculating expected value. Now, how can it help me in my pursuit? Now, do you remember what we just figured out? We figured out the cumulative distribution, right? We figured out the cumulative distribution of L. And I don't want to take derivatives and then multiply it by stuff. I'm going to just straight away begin to work with this cumulative distribution to find expected value of L. So the expected value of L is what? It's just simply the integral. It's the integral from A can be as, it's non-negative, so it's from 0 all the way to what can A be? The distance cannot exceed R, right? Of what? Of the cumulative distribution at L, 1 minus it, dA. Agreed? Yes, and then look at this. This is easy to integrate. This is simply integral from 0 to R of 1 minus A divided by R squared dA. And what are we going to get if we integrate it? If we integrate this part, we just get R. From 0 to R, it's just R. And if we integrate A over R squared, what are we going to get? We are going to get A over R cubed, right? A over R cubed. So it's minus, and then we can plug in R there. So, or you just maybe best we just, maybe it's simpler if we just use U substitution. So what is this integral? If you make a U substitution, A over R, you can say that this integral is the same as R integral from 0 to 1, 1 minus U squared du. You see what I do? I just make A over R equal to U, and therefore du is equal to 1 over R dA, and I only have dA, so I multiply by R. Yes. So that's the integral. And what do I get now? I now see this is R multiplied by 1 minus, what is this? This is just 1/3. So I now have 2/3 R is my answer. So that's one way to do it. Make sense? Good, guys, or am I just saying it to myself? Make sense? You can do it other ways, of course. Here are some other ways. So you can, of course, do this procedure. You can figure out the expected value by taking the derivative of the cumulative distribution, right? The derivative is 2A over R squared. And then what you do is you multiply it by A. So 2A over R squared, you multiply by A and integrate from 0 to R. And this way you still obtain the same exact value. You see, I mean, it just, but which is better? It seems that the previous process is better because here I have to differentiate and then multiply by A. But in there, I already skipped it, okay? So you should think of two things, guys. As soon as you see cumulative distribution, you think right away, I can use it directly to calculate expected value if I want to. Or if I'm afraid, I can take the derivative of the cumulative distribution, obtain the density function, multiply the density by the X or whatever value, you know, the values that we are trying to find expected value for, and then integrate it again. So you see, you differentiate, multiply, integrate, as opposed to simply 1 minus and integrate. Good. And alternatively, you can also do this, and that is just without converting. Let's say I want to calculate expected value of L, and I did not bother converting it to one variable. So then I remember, what is L? L is root of x squared plus y squared, correct? And so what do? I just take that value, multiply by density, right? dx dy. That's the other way of calculating expected value. Remember, right? One where we did not group together all values of x that are under the same label, right? So before it's just we have labeled a bunch of points and we add up for each label. Here we just add up for each x. So you understand the difference, right? Just different sorting of the addition. And that's what and then we need to change coordinates because it's all a circle and we don't like lots of roots. So we can describe this region as a circle. And when we do so, we just replace the x dy by the r d theta. And of course, we have to correct by multiplying by r. And then we have, this is r, x squared plus y squared root is just the square root of it is just r. So we have r squared when we multiply it by r. Again, you see this is r, change of coordinates is another r, so we have an r squared here, and this is the integral that we consider. And we again get 2/3 r if we do so. Make sense? So all those notions of calculating expected value you should have firmly in your mind. Here is another example. So we have a joint density function for x and y. And I want us to find the density function for z, where z is x divided by y. Make sense? Would you like to try it before I solve it, or would you like me to just go over it? Just try it quickly. S for solve it on your own, and G for go over it. All right, a lot of people just want it over with, right? As somebody said once, stop stabbing me, I'm already dead. So here's what we do. So I need to find the cumulative distribution. So that is what? That's capital F z at A. That's the probability that z is less than or equal to A, which is the same as x divided by y less than or equal to A, which is the same as x less than or equal to AY. So far good. And then I just try to interpret this probability. When is x less than AY? That means that, let's say, x can go from 0 to infinity, and y can go from 0 to infinity. And once I fixed up y, x is not exceeding AY. So x is from 0 to AY. That's the setup of the integral, correct? And what do I do? I then integrate it. Now I'm just doing two integrals. So first integral, I integrate the y and put, I integrate the x and put AY in it. Here it is, right? So that's the integral once I take the integral with respect to x. Now it's just another integral with respect to y. I do this process again. It's a bit unpleasant, but not too unpleasant. Those are simple functions. Once I integrate it, I get this expression. And once I'm done, it's 1 minus 1 over a plus 1. And now I just take the derivative with respect to a, and I get 1 over a plus 1 squared. Good? So this is my density function. Now we have a bunch of course, this is just a statement. There is almost nothing to say about it. Clearly, there is no reason why we should stop with just two random variables. We can have arbitrarily many random variables. Yes, and sometimes you do in applications. So we can have a cumulative distribution for many variables, just defined the same way. So if we have n variables, the cumulative distribution is just x1 less than a1, x2 less than a2, and so on and so forth. And the probability that this vector is in some region C is just the integral over the region C. right? So just instead of a box, you have a high dimension box. At least in theory, it's visualizable. And similar ideas hold for, I mean, it's almost a boring example. So you can see a multinomial expansion. Let's say we have several categories. So experiment consists in rolling a fair die 9 times. Each trial has 6 possible outcomes. Let xk be the number of outcomes where the die landed on the value k, where k is 1 through 6, right? So in this experiment, we just gather how many times a particular, we have 9 trials, and in each x1 through x6 tells you how many times did we gather that particular value. It's similar to a binomial formula, but it's multinomial, as you can see, right? Because we have more than 2 outcomes for each possibility. So this is, let's suppose we had x1 equal to 0, x2 equal to 0, x3 is 4, x4 is 1, and so on. That means that we had in all the 9 trials, we never had a single 1 come out, never had a single 2 come out. We had the number 3 came out 4 times, the number 4 came once, 5 came twice, and 6 came twice. Okay, that's what happened. So what's the probability of that? Well, that means the 9 trials, each of the 9 trials, each trial is assigned to one of those categories. You agree? I mean, the 0 category means nothing assigned, essentially. So 4 out of the 9 trials are assigned to deliver the outcome 3. 1 of the 9 trials is assigned to deliver the outcome 4, and so on and so forth. And the probability, of course, of each individual outcome, let's say probability of getting an individual 3 is 1/6. So 1/6 to the power 4 is the probability of having 4 of them. Yes? Independent, right? So it works exactly like a binomial formula. As you can see, here is the coefficient. So it's 1/6 to the 9th power. It's always going to be 1/6 to this power, of course, because each outcome is equally likely, and multiplied by the number of ways of distributing, of course, the trials to the different categories. So it's a direct generalization of the binomial formula. You see, to more coefficients. You agree? It's like the multinomial distribution. Yes, guys, you all get it, yes? I mean, or am I not explaining it enough? Okay. Well, good, let's hope so. So now let's begin. We don't have too much time, but let's talk a little bit about independent random variables. So they are independent if, of course, x in A and y in B equals to the probability of the product of the probabilities separately. So the cumulative distribution, in terms of cumulative distribution, it translates to this, of course, right? Just you multiply this relation, x less than A times the probability y less than B. So the cumulative distribution breaks into the marginal distribution of A multiplied by marginal distribution for y. Yes, makes sense, guys, why that should happen. I mean, again, if you think about the discrete situation, you can imagine why that happens, right? In the discrete situation, you can imagine for each individual case, the condition based on conditional probability, you have this product happen, right? You remember how at least intuitively you prove it. Conditional on what y did, it doesn't matter what happens to, well, x is not affected. The probability of x is not affected by what the value of y is. So this is the central point to take. Okay, so that means x and y, and if condition on what y is equal to x is not affected, that is equivalent to this product formula. That's what we covered from before, right? Just equivalent. I would not immediately intuitively think of this as defining independence, but once I see that it's a statement that both implies and is implied by the conditional probability, it makes perfect sense. Yes, just to be sure, let me remind you, it's this, right? So if you look at the sentence, if you had probability of X given Y, right, that should be just probability of X. But this part is the probability of X, Y, X and Y, right, divided by probability Y, right? And then what you do is just multiply back, right? So you can see if this ratio is equal to that, that implies that probability XY is equal to probability X, probability Y. And you can go in reverse. Make sense? Yes. So this statement is so, and of course we should expect that if we have X is in A and Y in B, if we have independence, it's just a summation of, first of all, it's always a summation of all combinations of Y in B and X in A. And if this is it can be split into a product like this, then I can factor the summations apart. Yes, so that means that probability of X in A is not affected by Y being in B. Yes. And of course, in the continuous case, I wonder if you see it right away, the independence is equivalent to this property for the density function. Do you see why that must be the case? The way I see it, I view it in the discrete under the discrete lens. So suppose that we have the expression f of xy dx dy, right? So this approximately stands for the probability that X is equal to little x and big Y is little y. That makes sense? Yes, I mean, because with the dx, it means we don't have a precision. I mean, it means that for us, X equal to X means X is in some small range that I cannot tell apart. So for instance, when you select on the ruler, you select the number 1/2. You don't really exactly select the number 1/2 on the ruler. You just it's to the best of your ability. There is always some error. This is what you do, right? Your hand is shaking when you draw a point. So you're selecting a small interval. Even if you draw a very good point, it's really almost like this, right? So it's an interval. Yes. So if I have, what is f of xy dx dy? It's this region. You see, the height is not visible, but here is the x, here is the y, right? Somewhere in the plane where this is x and this is y value, right? And the altitude is over there. So let's say f of xy is just the density. So this means that that y ranges in here and x is ranging in here. So all of this region is identified with x. All of this region is identified with y. Good. So what is this? If we have independence, this means what? This is the same as probability that x is equal to x times the probability, you can say it with respect to a probability of y equal to y, which will translate into what? This will translate into f x dx, f y dy. This is just an indicator. It's a density function for the y variable. This is the density function for the x variable. Yes, and of course, then you can just take, you see, it should be equivalent. So then you can take this, and of course, this and that, and cross it out. And you see that you should have the density functions behave this way, right? So you should have the cumulative density equal to the product of the marginal densities. That's a necessary requirement. And yes. if X and Y are not restricted, if it's in a square, then or a rectangle, then that's sufficient. Yes. Now, I do not know if we'll see if I want to continue. I did promise you to mention something about a calculation that might be useful for your exam. Yes, so I might be good to mention, guys. Suppose that here is just a simple example, right? I sent you a video. It's a pretty good video. You should watch it, right? And it actually has a good motivation for the beta distribution, right? So, for instance, imagine that you have, you see a retailer, and the retailer has 100 reviews, and the rating is, let's say, 94%. Rating. Okay, so you want to know how good is this retailer, correct? So 94% is, you might say the retailer is 94% good. Maybe your guess is not bad, but maybe it's not correct, because I mean, this is not the true probability. Maybe it's not important for the retailing business, but whether it's 94 or 93 or 95, maybe it's similar for you, right? But in some cases, it might mean a big deal, right? Just an extra number, extra digit might mean a big deal. So what's the true probability? What is the true probability here? So the way you can calculate it is, you understand that it means that 94 rated as plus and 6 rated bad, right? So it's as if I took a coin and I flipped it 100 times with 94 successes and 6 failures. And what you're interested, because you don't imagine yourself, you're not a millennial, maybe you are, I'm not sure, you don't imagine yourself to be the center of the universe, and you imagine yourself to be just a random guy, just like everybody else. Yes, that's very important, because I mean, if you're not a random person, you know, maybe it doesn't apply to you at all, right? But if you're just like those reviewers, just a random person, just a flip of a coin, then what's the probability that you'll be satisfied? What's the probability that the next toss of the coin is it will be a plus rather than a minus? Yes. So how do you calculate it? Well, you calculate it as the integral. I hope you understand why. Between 0, 1, the probability, it can vary, I'm not sure what's the true probability. The probability raised to the power of 95 times 1 minus p raised to the power of 6 dp divided by the integral from 0 to 1, probability to the power of 94, 1 minus p to the power of 6 dp. That's the ratio that you need to calculate. And if you understand how the conditional probability, if you want to, I'll explain how it appears, right? Then this is going to be your number. As it happens, it's easier to calculate it if you have here, if I introduce here the number 101, so it's 101, choose 95, right? And here I introduce 100, choose 94. Yes, if I had those red numbers, then what is that going to equal to? If you add those red numbers, this is just going to be equal to this top number. If you remember from the development of beta distribution, this top number is simply equal to 1 over 102. And this number is just equal to 1 over 101. So altogether, this is 101 1 divided by 102, this ratio, yes? So what you need to do next is you need to, of course, take those two numbers and simplify. You say, so you don't need the red numbers, you need to multiply by the reciprocal, yes? So what is actually 101, choose 95, divided by 100, choose 94. So that's going to be 101 factorial divided by 95 factorial, 95, and then 6 factorial divided by 100 factorial divided by 94 factorial and 6 factorial. Yes. So right away you can see the 6 factorials disappear, right? And a lot of things can be simplified there. What do you get here? You get 101. Now I cancel this thing out. And here I have divided by 95, right? So the answer is 101 divided by 95. So what do I need to do? I need to take 101 divided by 102 and multiply by the reciprocal of this number. Yes. So what I have is from before it was in red, so it was 101 over 102 multiplied by the reciprocal of the number, and that was the reciprocal was 101.95, correct? You can see it over here, right? So what do we get? We get simply 95 divided by 102. That's the probability. It's 95 divided by 102. So in essence, what do you do? In essence, if you can now do this very fast. You don't need to do the integration. Do it a few times to be sure. I mean, I would have forgotten it, right? But it means this. So if you have 94 and 100, what you need to do, you need to add 2 to the 100 and 1 to the 94 and take the ratio. And that will be the same as taking the integral. Isn't it nice? Right? So instead of doing this integral, you can just very quickly figure out that it's equal to 95 over 102. Good. So you can imagine, maybe you can remember it by assuming this. So what you do is you had 94 successes, right? So the probability is the same as if you add additional 2 outcomes, where one is a failure, where one is a success. Yes, one is a success here, right? Good. But you derive it. I mean, I would have forgotten this formula easily. You can just derive it. It's also will keep the beta distribution in your mind. It's my favorite distribution. I almost made the full exam about the beta distribution, right? But I also included other things. All right, guys. So yes, I'm going to the next page. Don't worry. Here it is, but just derive it. It's if you just recall how the beta distribution is produced, and if you understand how the formula is calculated, you can actually figure certain integrals pretty easily. Well. All right, guys. Well, thank you for waiting. If you feel like you have no questions and you want to go home, goodbye. And if you have questions, you can stay. We can talk about stuff. Right. Have a good one. I'm stopping the recording.